Well, I think the functional form and the relationship between the cross entropy and the software is very obvious because it's all calculated in terms of logarithm.
So you're using the KL divergence because that is the maximum likelihood estimator. So the cross entropy is a particular case of the KL. So the cross entropy minimizes the KL divergence in the case of multi-class classification, for example. So it's the same optimization problem, the cross entropy and the KL divergence, but the cross entropy is quicker to calculate. If you want to do a more general problem, you have to minimize the KL divergence.
Aren't they both just distances between distributions?
Yes.
I would have thought.
But so when you go down to why the cross entropy works for multi-class classification, you start with the KL divergence of the two distributions, of the predicted distribution and the actual and the ground truth, and you can prove that the optimizing the cross entropy is the same, so minimizing the cross entropy is the same as minimizing the KL divergence.
Optimized solutions are the same in both.
Yeah.
I see.
They are exactly the same.
Oh, okay.
So
That's a good reason, no?
I think learning on KL divergence probably makes the model way more all the learning set. So there's some more interesting experiments on some unspecified data set. The models are 8 layers. They're a little bit more interesting. What they do, however, is if I can find it somewhere in the page. Here it is. So what they do is they train one model, then they train another 10. So the 10 is an ensemble with variations, different initializations, of course. I don't know if they're varying hyperparameters. It says that they tried varying the inputs, so doing something similar to bagging, for those of you that are familiar with ensemble methods, and they said that it didn't make a difference. But basically what they're doing, they're training 10 of these models, and then distilling the results of the ensemble to the single model. So this is kind of interesting because we initially said train a cumbersome model and then a smaller one. What they've actually done is they've trained 10 of them and then trained one of the same size as the original, which is actually a pattern. A lot of people do this. I've done this before as well. It's one quick way because you know that, otherwise you have to do hyperparameter search again, right? You know that this structure learns on that problem. If you do 10 of them, it's very wasteful. We know that. And then you distill it back down. But the point is that this model has a better accuracy on the baseline than the baseline, sorry. Before I get into the ensemble bit, I wanted to talk a little bit about generalization. So they make the statement, can't remember where it is. Let me see if I have it. They make the statement about objectives somewhere in the introduction, which is that the training should reflect the true objective as close as possible, usually, but actually what we should aim for is generalization. So their argument is, I'm going to find the exact sentence because it is a bit, in my mind, a little bit controversial. They're saying it would clearly be better, well, not the sentence itself.
Second page.
Yeah.
You got it?
Yeah, thank you. It would clearly be better to train models to generalize well, but this requires information about the correct way to generalize, and this information is not normally available, right? So that relates a little bit about the thing that I said about transferring the regularization across, right? Because generalization kind of depends on regularizing correctly, rather than fitting well. And they're saying that when we're distilling the knowledge from a large model into a small one, however, we can train the small model to generalize in the same way as the large model. If the cumbersome model generalizes well, because, for example, it's average of a large or somewhat different model, the small model trained to generalize in the same way will typically do much better on test data than a small model that is trained in a normal way, right? This is the thing that we've observed. But if you think about it, and there's, I'll talk about it in a separate setting. You can think of the distillation process as regularization, because like a reduction in size can be considered regularization, right? It's kind of intuitive. And so saying that it's the point is saying that you're transferring the generalization, I think, is not correct. You're attempting to transfer the generalization, but you take a penalty is more correct, right? They go then into a bit of a discussion about the fact that we tend to think about the knowledge in a network as its weights, right? What does the network know? Well, the weights or the parameters that it's learned. Whereas in reality, the thing that it's learned is that G, the function, right? The mapping. We don't care, and like most of us don't care about what's in the weights. We care about how the mapping happens. So that's their justification for take those two things and move them into G prime. Yeah. So I think let's take a breather 1 second. Yeah.
Sorry, quick question about the table 1. The improvements look tiny. I mean, did I misunderstand something there? Or? On page 5. Table, yeah, there.
This one.
Yeah, this looks tiny to my.
It is tiny. It is tiny, but this is saying that to kind of like forget the baseline for a second, right? The thing to observe is I've trained 10 models, well not me, but the authors trained 10 models, and then I can reduce it to one model without much loss.
But do they know that 10 models is significantly better than baseline?
Yeah, they actually, so they make an argument there about, so the whole argument is about deploying the model, it's not about training. They say, assume that when you're training you have Google's infrastructure, so you can train whatever you want. But when you want to deploy, you don't have the infrastructure, so you need to make a compact model. So what they always, like they try to bang on is that the distilled model performs just as well as the massive model, but it takes significantly less resources. So I think in this one or in the next one, training the baseline model took something like 6 months, and they trained the distilled model in a few days, something like that. So
yeah. The point is, you reduce the size without loss of generality. Right? So the reason why it's tiny